Hello, my name is Danesh Shamsi. I am in section M07, and today I will be discussing my code in Visual Python that models the motion of a star around a black hole due to gravity. Overall, the main goal is to successfully calculate the mass of the black hole based solely on the position data of the star. Here is all the position data of the star that I was given. I'll show how this was used in the Visual Python code to calculate the mass of the black hole. At the beginning of my code, you can see that I inputted the mass of the star as 1.989 times 10 to the 30th. Additionally, the time step is equal to the amount of seconds in one day. So, as stated, for my code I was given a specific set of data, so I imported all the position data in this function right here in my own CSV file. Now, because I'm given position, I can use these positions to create position vectors that will allow me to calculate the velocity of the star. This section of the code right here creates an array of the calculated velocities that can later be used in the code in the momentum principle. So, I'll skip ahead and show that this section of the code is where the momentum principle was used. Here you can see that the velocities that were previously calculated were changed into the initial momentum values and the final momentum values within the while loop. Now, it must be known that the momentum principle can be split into both parallel and perpendicular components of momentum. It is important to note how these components directly relate to the parallel and perpendicular components of the net force. As you already know, the change in momentum over the change in time is equal to the net force right here. So it can be assumed that the different components of momentum, both parallel and perpendicular, are actually numerically equivalent to the parallel and perpendicular components of net force. However, the momentum principle shows us that they are different theoretically, and this is because the components of the net force due to gravity between the star and the black hole in this situation are what actually caused the components of momentum to even exist in the first place. So knowing this, I set my Fnet perpendicular and Fnet parallel equal to the perpendicular and parallel components of the momentum. So here I'll show you what happens when I run my code. The yellow ball was the motion of the star, and the three arrows represent the components of the net force and the net force components. The blue arrow that you saw was the parallel component of the net force that points parallel to the path of the star. The red arrow is the perpendicular component that will always point towards the black hole at all times, and the black arrow was the resultant net force between the two forces. These were all created knowing that they are numerically equivalent to the momentum principle components. This allowed me to visually show you guys what happened to the star. Now, using Newton's law of gravitation, that the force due to gravity is equal to the gravitational constant multiplied by the mass of the black hole and star divided by the magnitude of their distance. Right here, I used algebra to manipulate that equation since we do know since Fnet is due to the gravitational force, we can use algebra to manipulate that formula and set it equal to the mass of the black hole, so we can calculate it. Now, when the code was run, I had it display the calculation, and it can be seen that the mass of the black hole is 3.0047 times 10 to the 31 kilograms. Now, it is asked, what if the black hole was replaced with a completely different black hole of possibly different mass, but the star data position was exactly the same? Could you calculate the new mass of the black hole? The answer would be no. This is because all the calculations that led up to being able to calculate the mass of the black hole directly depend on the position of the star. If the position of the star remains the same, the computational model cannot take into account that the mass of the black hole is any different at all.